Welcome everyone to this week's FPGA, this month's FPGA seminar. We're really pleased to have James Ho from Carnegie Mellon University. He is a professor and associate department head there. He received his PhD in EECS from MIT in 2000 and his Bachelor of Science in EECS from Berkeley in 1992. He's interested in many aspects, as you'll hear, of computer architecture and digital hardware design, including the specific areas of FPGA architecture for computing, digital signal processing hardware, and high-level hardware design and synthesis. He co-directs the Computer Architecture Lab at Carnegie Mellon and is affiliated with the Center for Silicon System Implementation at the Carnegie Mellon Scilab.
Okay, thank you. Thank you. Now I heard you read that out loud. I can't go back and edit it, make sure it's up to date. Well, thank you for having me here. It's a pleasure to be here. So I am James Ho from Carnegie Mellon. So today I'm going to talk about this. This is actually it's a very sizable project at CMU right now. It's a new, think of it as asking the question, what should FPGAs really look like if we meant for them to be used as a computer, for a computing device, something that will sit next to a CPU on a memory bus, and not this thing with performance ASIC. Okay, and the work I'm presenting today is based on based on Eric Chung's thesis, and a lot of it is also based on the presentation that he made at FPGA 2011. I hope all of you went there. How many people here is FPGA?
We're at FPGA.
Is everybody FPGA?
You mean at the conference?
No, like your work is FPGA focused. Pretend you didn't go to the conference, it's okay. Okay, so before I get into the main part of the talk, I do want to kind of start set the landscape, okay? And most of the time when you ask, what's going to happen tomorrow, what's going to happen next year, what's going to happen 10 years from now, right? It's very hard to know, right? But being a involved in computer hardware field, right, we have this very nice crystal ball. Anything you want to know about VLSI, right? 5 years, 10 years, even 20 years from now, it's actually pretty reliable, right? Particularly, the crystal I'm referring to is an international technology roadmap for semiconductors, okay? And for the younger people in the crowd, it's not really a crystal ball. The reason these data are reliable is because these things that will come on 5 years, 10 years, right? The stuff 5 years from now is probably in the lab already. They need to finish it up. And also, right, the stuff that's further out, there's a very strong element of self-fulfilling prophecy, right? But for whatever reason, right, it has been quite reliable. And if we go to the 2009 version and ask, right, will we get more transistors? Will scaling continue? And what they will tell you, they actually predict out to 10 more years, which will stop in 2012. And what they will tell you is yes, right, Moore's law will continue. By 2012, there will be a 11 nanometer node, and we're going to be able to have approximately 16x the area density that we can get today. Okay, so great, right? More transistors. But what they will also tell you is, if you ask a question, right, what else is changing, right? And you will know they will tell you that this thing with VDD, right? VDD itself is not scaling any further. Okay, and so the main consequence of this is that, right, while in getting 16x the area density in transistors, right, the power density doesn't decrease as quickly. Okay, so if you're working within a power constrained, cooling constrained design environment, in order to get more performance, out of these extra transistors, right, the requirement is to go faster and use less power. Something kind of counterintuitive, right? More power, go faster. I understand, right? How do you go faster, but at the same time be more frugal? I think that's been the hard problem for everybody. And so I ask this question right now. It's like, okay, we know by 2012 we're going to have 11 nanometer node. If we take a very large die, say 500 millimeters square, there'll be 10 billion transistors on there, right? What will you do with it? One thing we can tell you right now is you probably won't be able to switch all of them at the same time, okay? But then this question is also, in this power-constrained environment, what do you do, right? The classic big superscale oligo core, that's not going to happen, right? We may have one, okay, but that's not going to be what's going to use up all the transistors to give you performance. People are interested, lots of little cores, right? You might integrate a GPU, right? I'm here today to tell you I'm interested in putting FPGAs on there, right? And one thing I'm gonna try to convince you is first part, how's an FPGA, right? You guys actually, might appreciate already, FPGA is actually a very capable computing platform. And one thing that kind of surprised us in the last 2 years is that it's actually quite capable even for floating point applications. So that, I'll show you some quantitative results on that later. And also ASIC, right? So lots of different things you can do. How do you know what to put on? The roadmap will tell us what the technology will do. I think it's still up to us to figure out the future, what's interesting to put on, what will make sense. And to make that decision, right, since it's power constrained, the thing we care about is performance per watt, performance per power, and to some degree also performance per area, because I think area will still be some limitation. So to answer this question, right, we did work like last year where basically we want to ask, right, how do all these different technologies match up to each other? And so the way we did this, we just went and bought the best you could buy in 2010 timeframe. CPU, GPUs, FPGA, and ASIC technology. ASIC actually, the stuff that we can actually write papers about isn't quite the best. 65 nanometer is what we have access to. But at the end, I'll normalize this number to make it all 40 nanometer. So, but this is, except the ASIC part, right? This is kind of what money, what the best money can buy in the 2010 time frame. Okay, so you have the Intel Core i7, right? This the new NVIDIA GPU, the ATI GPU. I included as well the previous NVIDIA GPUs because it's there we can use it. Okay, and also kind of the largest Xilinx part available at the time. Okay, and here's some basic characterizations. And for these, we want to do a best effort implementation of different applications. And so for each one, we choose 3 applications: matrix-based multiplication, the fast Fourier transform, and the Black-Scholes algorithm. This is for the arbitrage pricing. And all these, right? We could have chosen something with lots of XORs, right? But that would be, we already know FPGA is great at that, right? The one thing we're interested in, so if you want to compute, let's do at least do single precision floating point, okay? And so for the CPU, we're able to find, so both from using a combination of vendor library and research project, right? We can find, sort of the best implementation of these benchmarks. And also notice that, right? We're being fair here. This is the best we can buy, and when we get it, we use all the cores. So these are all multi-thread implementations, right? This is the best you could do on that chip at that time, right? So NVIDIA, this is the cuBLAS, right? So the implementation of the vendor implementation of those things, and also for ATI, there wasn't a standard library, but at least for mission multiplication, we were able to find this very fast implementation that was open source on the net. For the FPGA stuff, unfortunately, Eric had to do all by hand, right? So, and I trust he did his best efforts. And even if he didn't, that's okay, because since we're pitching for this side, if he didn't do a good job, we're being conservative. Okay, so that's kind of the baseline for this first study: platforms, applications, and the implementation. And there's actually a lot of effort went into going about measuring, power and energy dissipated on those platforms. I won't actually get into that, but here's a summary of the result. Right? So here are the different devices, and for major multiplication. So again, this is the same application, best effort implementation on each platform, and you get about this, these kind of numbers. And what you see, right, very clearly is that, right, GPU, really does much better than what you could do on Core i7. But this is actually a very impressive number on Core i7, right? This is pretty much very close to peak number already, right? But as impressive as that is, it is a general purpose platform, and general purpose has a high cost associated with it. So if you go to GPU, this is probably one of the nicest things you could compute on GPU. You get these huge numbers. In particular, notice that, right, this was, we thought for sure that was a mistake. This is 1.5 teraflop. Actually, this is not estimate. We actually did this, measured it. 1.5 teraflop on one chip from this ATI chip. On the Xilinx FPGA, okay, not quite GPUs, but certainly, right, certainly clearly better than CPUs. And keep in mind, we're no longer talking about doing cryptos and XORs and things like that. This is actually single precision floating point operations. Now, this is the absolute performance, but we're talking about fitting things into power, fitting things into die area. The thing we care about is really, how do I use up my budget? So we should really be normalizing, right, the performance to area and performance to power. And here to do this study, we did normalize things to 40 nanometer. Okay. And now things start to look a little better. And for this study, right, we also, what we did, we took the same FPGA design, right, and just mapped the 6 nanometer center cell. So this isn't the best you can do on an ASIC. It's what would the same design do on ASIC. So in normalized sense, this makes sense. Again, right, well, a few things that jumps out at you. So obviously, right, doing things hardwired in ASIC in transistor is the best you can do, be the most efficient in terms of area and power, right? CPU, in order to be pretty good on a lot of different things, right, they pay a huge overhead, and so their performance per area, performance per power is lower, much lower than everybody else. And here you'll find that, right, you're now in this world, okay, right, yes, there is, FPGA has a large interpretation overhead, right, you're still mimicking, right, you're not quite working at the native hardware level, and you think of what GPUs really are, these are just a bunch of floating point units. They're going to be very, very efficient, right, in terms of area and power, but, right, so, but now if you come over to this, operation per joule, or the same thing, performance per watt, you find that, right, not only does, FPGAs do have very respectable performance relative to CPU, right, it's also, very energy efficient, right, better than CPU, at least in the same neighborhood as GPU. And one thing I'll claim, right, is that, right, we don't actually have to beat GPUs, right? FPGA has its own advantages. This is major application. This is a good point. This is one of the best thing, easiest thing to run on GPUs. If you move away to different applications, for example, something less regular. Actually, I have this, right? You look at some things like FFT, right? Once you fall away from what's natural on GPU, they degrade. Okay, whereas FPGA being reprogrammable, we can always tailor for other things. And also FPGA being, some sort of clean slate, I can go after all kinds of different parallelism, whether it's task level, spread level, instruction level, even the bit level. Okay, and so here I'm just showing you sort of different, two other applications, fast forward, transform, block show. I won't go into details, but generally speaking, he's pointing out that I think, right, I'd be fair to say that, right, it is definitely worthwhile to consider FPGA, the reconfigurable fabric, as a viable computing technology, processing substrate. Okay, and if you're interested in more about just the data points, you can go take a look at our micro paper last year, and the paper will give you more details on exactly, on how the measurement was done, and also the paper includes using some models to speculate, what things will look like 10 years from now. Okay, but here for today, that's today. Okay, and fine. Okay, you guys already believe in FPGAs. How people use FPGA for computing? Not necessarily. How people use FPGAs for computing? Practically nobody.
We do.
Right. But not everybody. Do all we love it. If you ask the general population, they say what? FPGA is this thing you build hardware with. You put it when you can't afford ASIC, you make an FPGA, right? And right, what's wrong with it? It's such a powerful thing. Why isn't it being used more? GPU is being used quite a bit already, right? In a few short years, it is becoming, it's, at least in the supercomputing world, that is today the dominant processing element. And the problem I think kind of boils down to it. We found this citation from Andre Dahan. This is actually printed in the proceedings, so we thought we were very impressed. Right? If you go to IEEE Explorer, you will find this. Right? Traditionally, FPGA had been the bastard stepbrother of it. I think that captures sentiments very, very well. Right? Throughout its lifetime evolution, it's always been designed and improved again and again to be a better alternative to ASIC. the fabric is very, very powerful, but it's just never been done to be something on a memory bus, to share the workload on a CPU, right? So what we want to do is kind of visit that problem to say, actually, we like the fabric, but what else do we need to add, to change, so that it becomes an appropriate computing platform? Okay, so that's kind of just kind of motivating why people should actually. I kind of delete that whole section. I'm in Toronto. We believe in FPGAs. Okay, so now I'm actually going to tell you about what the CORAM project is all about, and then I'll I'll show you. And it is still early work, so I'll show you some of the current work and evaluations we have, and then I'll conclude. Okay, and again, I guess I could have deleted that. You guys know what FPGAs look like, right? All right, so sea of gates, right? So rather than having transistors where you have these tiny lookup tables, and you use lookup small SRAM to implement combinational functions out of that, right? And some of the stuff you do harden, you want lots of floating point, flip-flop for states, and then you just route this interconnect that's that's reconfigurable too, and this I'll loosely refer to as the fabric, and logic map onto the soft logic. Okay, so that kind of like give you generality, but you do pay for this interpretation overhead. What I've been told roughly 10 is pretty much close to 10x in every dimension I can think of. Okay, in terms of area, power, performance, etc. Right, modern FPGA usually have some additional stuff that's being hardened. The one thing that happened early on was this big memory. Memory was very expensive to fake. Right, you can actually take very little area and produce a lot of memory that you could use. Even if you don't use it, it only takes up a little space. And when you need it, right, this can replace a lot of the soft fabric space. And now, the newer ones will also have things like the DSP slices and stuff like that. Okay, and that's what brings us to the fabric itself being right. I'm happy with the fabric. I don't want to redesign the fabric, right? And so the context of our work is we want to have FPGA be an equal partner to CPUs. So whether you're thinking in terms of in a system you have FPGA and CPU on the same bus, sharing the same kind of memory bandwidth and connectivity to main memory, or in a heterogeneous multi-core, having FPGA being one of the cores. Again, also sharing the similar kind of performance and connectivity to memory. Okay, and in this way, they would collaborate and communicate, pretty much in the shared memory way. But that's right. So think, if you don't have anything else in mind, have that as a mental picture on, what FPGA computing on FPGA means. Okay. Now, let's just think about this. Right. So you guys, some of you have done application on FPGA, so you guys can probably, appreciate what I'm going to show about next. So here is my FPGA, my clean slate, and my I/O path. That's pretty much what they give you. What does it take to build an application? So you begin by building some kernel, like stuff that accelerates well in hardware, has kernels repeatable, and we optimize it, we build it. Okay, and usually when we build things as a hardware person, when we think of a state, we like to think of things sitting in these nice SRAM, these block SRAM, whatever. My application talks to these tiny SRAMs. Okay, and I will always claim to my software colleagues, right, doing this kind of work as a hardware person is no harder than asking asking to write a equally well-tuned software kernel. Okay, I can do it just as well and just as fast as someone else could do. Again, this is not writing hello world. This is writing a well-tuned. Imagine writing a well-tuned kernel to run a GPU. It's not sitting down writing one line of code. It doesn't happen like that. But anyway, this is certainly not. This is definitely not the hard part of the application. In fact, if you go look at FPGA proceedings, a lot of publications are based on implementation like this, and to show you lots and lots and lots of performance, right? If somehow data magically showed up on chip in these SRAMs, then my kernel would do so well. But the problem is, in building real application, you never stop there. Real application, you talk to data. So, right, I need to go outside. And on today's FPGA, we start talking about building a memory controller. You can, right? But the problem is, again, you pay for the interpretation overhead. On a GPU, I can get about 200 gigabytes per second. On a CPU, 60, 50, high tens is easy, right? Once I start doing soft logic, even the best I can do, we're talking about maybe a handful of gigabytes per second per channel. So altogether, right, 3, 6, 10 gigabytes peak, right? You can do it, but already you just cut yourself off at the angle right here. And it doesn't stop there, right? Because this is just at the edge. I still need to bring things in. So I need somehow be able to distribute data from the edge of the fabric into the fabric where my kernels are, and my kernels tend to be, there's lots of them, and they'll operate in parallel, okay? And so this network to build, and then I gotta go and build the control logic to orchestrate everything, okay? And at least it's certainly true in our experience. Building this is great, showing great performance here is great. When you actually start talking about building a real application to deploy, right? What ends up determining how well you can do, it's all in here. How good a job can you do in your data movement part of it, which has nothing to do with computation. And this is what I mean by FPGA is not done correctly for computing, right? These are the things that we obviously need, they don't exist. So let's try to fix things a little bit. So memory controllers, if you're computing, you need memory controllers, okay? And in fact, Vertex 7 already announced they have memory controllers, not a very fast one, but they have some. But you can certainly imagine if I'm building a dedicated device for computing, I will hardwire a memory controller. Why should I pay 10x area and speed so I can have flexibility where I don't need it? This data distribution thing, sorry. And so we replace the memory controller by simply a memory interface at the edge that allows me to talk to DRAM. Now for data distribution, I also get rid of that. And we talk about computing, we're talking about moving data around, putting a network on chip, right? Because no longer am I worried about, can I route this long net from this corner to that corner because RTL says so. That's not what this FPGA will do, right? This FPGA is about supporting these kernels and feeding it with data as quickly as possible. Then I can, I build an NOC, right? And the benefit, in return, you get a huge benefit, right? Because by putting these network, even though it's less flexible, it's hardwired, it only does one thing, but it's so efficient, right? I can use very little area and just simply over provision and perform so much, it'll be good enough for almost anything you want to do. Okay, so you really shouldn't think of it as being more restricted. Right? This will outperform anything you could build custom in the soft logic. So, I think that's basic evolution. Anybody who starts thinking, that's where you would head, right? So this next step is kind of where we saw two things leap in our thinking, is like this control logic. Here's my compute, here's my data movement. Who controls it? Right? And actually, when we first started, we were actually happy with here's my RTL for this, RTL for that. And then very quickly realized the stuff you do here, right, isn't data path. It's finite state machine, and it's not performance critical finite state machine. So why don't we, think of it as threads of control, right? This is software in quotation. I'll tell you why software in quotation a little bit. But think about writing software threads where you can very naturally deal with pointers, deal with moving things, and dealing with control flows, and not work with finite state machines or RTLs. Okay. And the reason software is in quotations that I want you to think software, think threads. It doesn't necessarily mean I'm going to compile it to run on a processor. But for now, picture, this is how you so when you develop application, right, this becomes your abstraction. All that stuff that locks you into a particular FPGA family, a particular board environment, it's gone, right? You as an application developer, do your kernels, the stuff I enjoy doing, you enjoy doing too, talking to these simple SRAMs, and never have to worry about how the data get there. They're just there, compute quickly, right? The responsibility of actually making data available and also orchestrating the overall control flow, now let's think much higher level. Just write software, right? And whereas on this side, things have to work on a cycle-by-cycle basis, where you really have to operate at a very low level to be efficient. On this side, it's much more bulk transfers. And having a loosely synchronized thread level thinking is very appropriate. And the elevation abstraction helps a lot when you start talking about optimizing, changing the scheduling or changing the high-level organization of the kernel. Okay? And this is what we're really talking about. CORAM is not so much a FPGA architecture, it's more like an abstraction. It's more like an ISA, right? You as an application developer start working with this. And the hope is that whatever you develop here will become now portable to any FPGA that supports this abstraction. It may even be multiple FPGAs on a different board. Also, right, you can imagine by looking at this level of abstraction, I can also have scalability. I can certainly guarantee I can move a application to a new bigger part. And once I'm recognizing this more stuff, right, depending on how you actually use the abstraction, you can actually even scale up to consume the extra resources, right? So you're no longer, in the old days because we're working at this level of abstraction, right, everything's explicit. Whatever you build works on that part in that board, right? And when a new board comes out, you never port it, because right, it will take you 2 years, right? By then you need another board, okay? So this is it. This is what it's all about. So any question at this point? You guys buy it?
Sure. So that reminds me a platform-based design that I think people in the EDU will
yes,
have been,
yes, the structure.
advocating. So the question here is that are you advocating that building this kind of abstraction on the existing FPGA fabric, or you're advocating that you actually want to harden this part into the,
Very good question. I think. So I'll get to that at the very end. Right, this is a very hard question. This is right. This here is an abstraction. I don't say how to build it at all. Okay, and certainly this abstraction lends itself to either all hardwire, all soft logic, or some hybrid of either thing, right? And actually, so that when I start talking about the current work and results, that is the most interesting question, right? What do you hardwire? What do you not? Right? And one thing that I think I was mentioning a little bit earlier is this. I think NLC, right? Once this, I no longer care about mapping RTL to this chip, like big RTL. Then I think NLC makes a lot of sense, right? I can use less area, giving much more performance than you could ever do in soft logic. So in that case, it makes no sense to leave NLC. Now, something like this control thread, do I put a microcontroller down and really run software? Or do I compile my control thread into soft logic from my same machine? That's a very interesting question. Okay, so that I'll get back to that when I get to the result part of the talk. Any other questions?
Yeah, James. You typically design your application so your data is in those on-chip SRAMs at certain times, for example,
That's right.
at certain clock cycles.
That's right.
And how long it takes for data to get in there depends on the target board you're using, for example. If you have
Right.
DDR2 on your board or you have something else on your board.
That's right.
So maybe you're going to talk about it later, but isn't that a key part of does this abstraction sort of
That's
get rid
right,
of
right.
that?
But wouldn't you much rather deal with that kind of changes at this level? So imagine master and slave. These guys are really dumb, very local.
Yeah.
They only understand this. When this is full, we say, go do it. When you're done, come back and tell me.
So there's gonna be, you may be able to show it, but there's gonna be some handshaking.
That's right. And but it turns out, this variation in platform, right? You would never ask that question on an Intel CPU between Pentium 5 and Core stuff, whatever, right? That's because you're working at a much higher level abstraction, and that's taken care of with whatever happens to be the best implementation. We build it and obeys the abstraction. Okay, so I think, and so yeah, I do need to. There is more than SRAM. You do need to do more, and so this is kind of a very simple example first. So imagine here's my application, right? And we kind of picture just writing Verilog. Okay, you can use anything you want to design the kernel. I don't care about the fabric or the language for. Okay, at least not in this talk. So I like Verilog. We do Verilog, and you actually build your kernel, and you declare I want SRAM, and we call them CORAM. Which is want to be different. And also, this is kind of distinction. So we need to have some way. We don't want these guys, the kernel and the threads to talk shared memory. So we have to build communication channels between us. You can also declare, hey, here's a FIFO that connects me to my managing thread. So you build the processing part here, and you build this, and this thing doesn't understand where it is. It only understands this is the extent of its horizon, and you just optimize, optimize the heck out of it. And I actually enjoy doing that. And then I come over here, and I write in abstraction a thread, and the thread will begin by actually getting control of this CORAM. And so in my abstraction, I have a thread, I have my global memory, external memory. And when I want to move data, in the thread level abstraction, it's just a function call. Move from here to there, right? When it's done, tell the kernel to go. Right? That's kind of sort of kind of how you want to, generally think about how you build an application using this world. Okay, and in terms of sort of what actions the thread can do, so we, this basically, moving data back and forth between a CORAM and memory, right? We will want to be able to copy CORAM from one CORAM to another CORAM. So if you want to share data on this within the chip, you can do that. Okay. One thing that's very important that you look at VRAM. One thing that's powerful VRAMs, there are ways of combining multiple of them into a single large one, right? So we want to work with that too. So even in what we call CORAM, they're really just VRAMs with logic behind it. And we also want to allow you to combine multiple of them into a large, appears a single large memory and work with it in abstraction. So it's not copying just memory, one CORAM memory. You can actually copy memory and sort of a combination of multiple and view as a single CORAM, right? And also, because application, you might want things like gather and scatter, sharded accesses either on the way in or on the way out. Okay. And actually, so one thing you want to also think about. So we're talking about programming threads, right? So this is also the issue of ordering. So right. All these things will have a blocking and non-blocking version of function call, and for the operation, there's also order and non-order versions of the operation. But I think that's a little bit deeper in the abstraction. But right, so imagine writing programs and telling the kernel to go and do things. So that's taking a look at something a little bit more detailed. Right. So here. Image multiplication. So imagine everybody here, at one point or another, has done image multiplication either in software or hardware. Okay? So if you haven't, right, it's 3 matrices, and what you want to do is, right, you're going to multiply A and B, right, for every point here, right, you want to do a dot product of the corresponding, column and row. Okay? And so, it's not hard to imagine what a kernel for this application would look like. It's just a dot product engine. Right? I have data streaming in, and I do a dot product, I accumulate. Right? That's easy. And whether it's Verilog or C, right? It's no harder one versus the other. Right? The problem is what comes afterwards. To actually do a good job of multiplication, which Eric had to do, right? well, we have to wrap that kernel with everything it needs to talk to the outside world. So I can actually get to, so the data have a way of getting in, I have a way of asking for the data. And have, and buffer and then wait for it, right? So but that's only one engine. In a real design, I actually have to do multiple of them. And all of these, I have to synchronize and manage and, get it all to work. So starting with the kernel, right? This is where you end up spending all your time and so ingenuity in designing a good application rather than a good kernel. Okay? Let's think CORAM. This is what it will look like in CORAM, at least, right? What the developer sees. Here's my dot product engine. Okay? And here my input output SRAMs are CORAMs. So I have the luxury of not worrying about how data got in there and how things will leave. I just do my dot product, then I'm done, right? And my interaction is, hey, I'm ready to do another one. And from somewhere in the environment, go ahead and do another one. That's the extent of the kernel, but at least a simple one.
Okay. Where would blocking show up in this?
What do you mean blocking?
Where the matrix is really big and you want to bring in sub pieces and
Yes,
and
no, so
features.
you can deal with that as well. So you can imagine instead of having just a dot product engine, this could be, you can build a block matrix multiplication engine, right? So whatever will be the kernel, that's what you build, right? So actually, we'll come back to this. That's a really good point. So here's my control thread for this, and actually, can you guys see my pointer? Okay, right. So for those of you who have written matrix multiplication software, that looks just like software. You have your tripling nested loop, and all you're doing is going through the row and column and collecting them. And here we also need a third loop because we're not assuming we can do all of it at the same time. Right? But here, right, basically go through the loop, right? You tell, so you wait until the FIFO say, hey, I'm ready to do another one. You bring the data over, okay, and then you tell it to go for it. Okay, and sometime later there has to be this, hey, I'm unloading everything. I'm not showing you that part yet. Okay, but let's think about a few things, right? So, okay, what if I want to have multiple engines now? I stem multiple of these out, but in terms of managing them, it's not any harder because in terms of understanding that they're not multiple engine and data has to be partitioned a certain way, you do that in the software. It's a software issue. Okay, you want to do blocking. Okay, then you have to build the kernels for the blocking kernels. But again, right, the point of blocking is all about reducing the working set to fit, right? So that's appropriate as a kernel, and that you can marry that kernel essentially to the same, right? Basically the same thread structure, right? The part about, okay, now that they want data has been presented, in different chunk, different order, different time, that's a software issue. At least it's easy to think about. It's very natural to think about those things. Control, scheduling, pointer manipulation, doing that in the software level abstraction. Okay? Okay, so that's kind of the high level pitch. Did I use up all the time already?
Yeah, we have the room for another hour, so. But lunch will show up.
Oh, really? Okay. So I don't have another hour. I just make sure. So okay, that right. So what I'm going to do is kind of show you the stuff that we've done. So, right. So, is CORAM a good idea? I think so, and I want to prove it. But again, this is what we had to do the work about, right? And I think it's one of those things where it's not, performance also almost doesn't matter. It's not about getting more performance, right? A big part of it, right? We do want to reduce power, but by computing on the fabric, I get that, right? What CORAM really does, it's actually about productivity, programmability, and portability. will people actually start writing applications to target an FPGA if it starts to look more like this? Okay, then, you know, fine, if it's, you know, will it get faster? Probably actually not get faster. So ultimately, I'm still computing on the same fabric. I might get a speed boost from having hardwired NOC and hardwired memory controllers. But in terms of the kernels will not get any faster by themselves. Okay, and again, area and power, right? That comes from doing things on fabric, right? It's about will people actually sit down and build applications, right? And so that's kind of big philosophical questions that we'll see by the time we're done, right? But some more tangible question we can work on is kind of this, right? This question I think was earlier, right? That's an architecture, it's abstraction. Now build it. How would you do it, right? And in addition to how you do it, it's hard, soft, hybrid. Okay, and then so that's how I'm going to touch on that a little bit more. And then there's also issues of how do you actually incorporate with other things, and then applications. Right? I showed you 3 applications at the beginning. There has to be a lot more applications, and I'm sure not all applications will work well with this. Not all applications will be parallelizable, right? And maybe some applications really just won't work at all. I can't partition it into this processing, data management kind of scheme. Hey, long time no see.
Yeah, so just to clarify really quickly, the original numbers you showed, were they end-to-end system numbers?
Which one?
FPGA, at the very beginning when you're doing the bake-off?
That's just kernel. That's just the fabric,
Okay.
right? Because the problem is, right, you will never be able to, the GPU numbers and CPU numbers are real. I can't get back there, right? They're real because they actually have memory performance, right? But on the FPGAs, I get 6 gigabytes per second. That's what I can get, right? And if you start with that, just forget it. Okay, so for that first time I reviewed the paper, we made everybody compute them. So all the problem sites were chosen. So it's all about how fast can you do the processing, because we're interested about fixing this stuff on the outside and the abstraction. So okay. Okay, so what we're doing right now, so I think Eric, this work is Eric Chung's thesis, and he presented this on first paper at FPGA this year, right? And ongoing, so it's actually a lot of activities. Actually, I started since last year, right? So we kind of have at least a first version of architecture, API, abstraction, whatever you want to call it, okay? And now it's actually about let's build a prototype so we can think through about all the details. So what Eric's doing right now, he promised he'll do before he graduate, is actually come through with a proper microarchitecture and an RTL implementation of it. And that will be available to drive all the other studies. Actually, one thing that's interesting is, right, he's actually committed to make that RTL available as a solved library. So for people who want to try it, you can always prototype CORAM on a regular FPGA to try out the productivity part of it. You won't get the performance benefit, but you can at least get a sense for the abstraction. Wei-Nam Ma is it's a student advised by my collaborator on the project, Professor Ken Mai, and he's a circuit level person, and he's actually looking at some of the special structures, right? How do we actually map? How do we implement those at the circuit level efficiently? Michael is another student, and he's actually interested in that on-chip data distribution network part of it. Okay, and Gabe White is actually asking this is one of the so I hit on this problem last because in the beginning we were just so happy with solving memory abstraction, and once we kind of understood what we're doing, we realized not only is abstraction easier for me to work with, it's actually easier now to compile to from a higher level language. So what he's doing, he's actually looking at using LLVM as a platform to be able to do parallelization and extract so partition of data and compute and do parallelization so that we can from a high level programming language target the CORAM abstraction. Okay, so these are kind of so I think multiple students at different level of abstraction. Kind of all looking at different pieces of the project. And, so what I'm going to do is focus more on what Eric's doing, this microarchitecture idea. So we talk about the architecture. If what is a way to build this? Right. So again, we go back to a clean slate FPGA, but now I'm just going to predict. Actually, it's not prediction anymore. There will be memory controller, and I'll predict there will be better and better, faster memory controller if we actually build a chip for doing this. So that's, I take that as a given. What we need to do is, right, these blockgrams, now we have to solve, right, they're now blockgram with special sauce behind them. So there's a logic behind them, and we do have to build the control thread structure and also this interaction with the global network and all the memory queues, and there'll be a lot of crossbars to make the abstraction appear correct. Okay, and so this is when I talk about microarchitecture RTL. This is what Eric is building, right? And I'll show you a more detailed picture of that, and then there's so the looking at the issue of global network on chip, and here this is actually I think similar to what Natalie's thinking. So we're building network on chip, but it's not just for anything. It's network on chip for CORAM, and the usage model, the timing, the way we use things, right? Just for the regularity of traffic, it's all specialized. And so it's rather than looking at general purpose network on chip, right? This will be something that cater to what we need in this environment. Okay. Right. So let's go take a look at this cluster design. So if you buy a Xilinx or Altera FPGA, actually keep on calling it BRAN. That's okay here, right?
Yeah.
So SRAMs, right? That's what you get. But in a CORAM world, the kernel sees that, but there's a lot behind it, and we have to build with that. And right, so first of all, there is a data path, right? This data coming out the network, right? We need to be able to direct it to different CORAMs, and because we want to support the gather-scatter, the ability to combine multiple CORAM flexibly, right? And then you end up introducing quite a bit of data path into it, and in particular, right, to have that full flexibility, there's all this basically big crossbar somewhere in there. Okay, and then there's the control part of it, right, having to do with the so the commands and the events arriving and scheduling it to make use of, right, this is essentially a router, and we need to allocate a schedule a router properly. And here again, there's all these logic having to do with the full complexity of abstraction. But you can already imagine, so this is to implement the full abstraction, every possible control action, right? If you come to an application that says, okay, I never do gather-scatter, I never need to combine DRAMs, then this very quickly, simplifies away quite a bit. Okay, and that's what leads into this question, right? If I do a soft, I don't have to build everything, right? And if I build hard, then I have to do everything all together. But it's actually not that straightforward, right? Because I think the thing that's missing in this picture is the cost. How much does this cost in transistor count or area if I were to put it in transistors or in soft logic? Right, so here's to give you an idea. So this is, right, if we, right, to build one cluster, okay, to build a cluster, right, so if we take the largest vertex 6 right now, and assuming we're gonna use every VRAM available on this particular chip as CORAM, and we'll group them into clusters. Okay, so every 32 VRAM becomes a cluster. We're going to build one of these things for it. Then you'll find that on this chip, on this vertex FPGA, we're going to spend 21% of the fabric just to build the cluster itself. Seems like a lot. Well, it's 1/5. It is, it isn't, but it seems very, very high. Okay, and you notice that where all the cost is going isn't this crossbar and this it's all these crossbars to support the flexibility of all the potentially require data path for the control actions, right? So if we say fine, okay, so if we simply limit that, you can actually only either always read, only write, never together, already we can reduce things, right? And if now you say, okay, I'm gonna make it application specific, you pick, I forget what application this is, but we say we actually only build what's needed by that application, then you can get it down to 10%. That actually makes it not too bad, even if I want to use this purely as a solve thing. Okay, but I'm not showing you the NOC cost. NOC cost will make it, right, so this is just for the cluster logic. Now, what kind of surprised us a little bit is, right, if we were to build all the cluster logic using transistors, okay, in terms of the area it takes up, that's less than 1%. In fabric terms. You understand what I mean? Right? The actual cost, right, if I only have to take away 1% of your LUTs if I can use those same area in transistor as hardwire logic to build the cluster logic.
So I have a question about that area number. So are you getting that by counting transistors, or are you running it through an ASIC flow? Because you have structures like crossbars here, which tend to be metal limited.
Right. No, so again, so we're not circuit people. So these are all RTL synthesized through Synopsys.
And then take the transistor areas that come with
Yeah.
that.
So you have if you're a circuitman, you have to apply your own interpretation on this. But this is based on what Xilinx synthesis tool and Synopsys synthesis tool tell us. Okay, like mapping to standard stuff.
I guess another question I have.
Right. But I don't think this will turn to 10%.
When you go, you have a 32-way crossbar
Right.
between your memory access unit and the SRAMs.
Right.
if I'm interpreting
I don't think it's 32 doesn't require 32-way, but it is proportional to that number.
Okay.
What's the question?
So I guess my question is, when you go application specific,
Right.
how much can you remove? It seems that many applications might be able to remove
A lot of it.
perhaps all of that crossbar.
Yeah.
So I guess there's probably a big space there, how application specific you can get. So
That's right.
When you went to application specific, how many things optimized away?
I mean, so here, right? So we did more than just say tie it to 0, give the synopsis. Okay, so this the student did go in and prove things out by hand. Okay, unfortunately I can't remember what application this was. Okay, but right, it's the you need the crossbar for, and it's used for multiple things, right? Because from one data stream come in, right, I need to feed it. Right, every cluster has a single network endpoint. Right, so data has to be distributed somehow. Okay, the question is just right, how flexibly can I move things around?
Thanks.
Okay. So anyway, it's not going to go away, but but it's right. But I think the main takeaway is right. Even if you think at least the cluster logic in complete solve terms, it's not ridiculous. And it's the overhead in car logic is quite small. This is kind of like the VRAM story. I just take some area, turn it into VRAM. I'll save you a lot of LUTs in case you ever need it. If you don't need it, you pay a little bit.
So, how much frequency max does it take away?
From what?
I mean, it's speed, right? So because
Who's
the raw
speed?
block RAM, you can run, for example, 400 megahertz, right?
Well, that's the thing, right? So if you go to ASIC, it's you actually get a speed boost too, right? When you map down, it's even 65 nanometer synthesized. They tell us 1.1, maybe half of that. But again, it's going to be much faster than what you get. So you get the area and the performance that way. Okay. Now if we cast it a different way, let's think in terms of in application terms, right? So here, imagine, right? This is matrix. Okay, now I remember now. So starting with the original matrix multiplication he did, right? And right, this was kind of the performance that he was getting. Okay. Right. So you have performance. It costs you 10,000 watts, and we use that as baseline. So roughly cut at 1x in terms of performance per area. Okay. And it's just FPGA is this, so 0 overhead. if we introduce the hard implementation of CORAM cluster, then we introduce 1% in area overhead, right? And we save, right? We save a bunch of LUTs, well, a little bit of LUTs, so the you know, we some of the data management part of it, okay, and performance goes up by a little bit, okay, but that's not what you're supposed to read, right? Performance doesn't matter, right? What I'm trying to show you here is, right, the difference is small, right? Or at least we don't lose a lot, we don't cost a lot more, right? Because remember the benefit is having the traction, being able to work within the traction. So that's so the comparison you want to pay attention to is the fact that it doesn't, you know, we don't suddenly double the cost because of this. Okay, and then now we can look at also introduce a solved version. Suppose, right, we're not going to get this new FPGA anytime soon. Let's just use RTL as a solved library to build applications, so that I can claim the productivity advantage. In that case, you end up paying, you know, you pay, you know, roughly 25% overhead in solved logic to build a CORAM cluster, right? So there's no extra die area, but I lose performance area, and right. But if I go to a prune version, I can reduce that cost.
Sorry, what's the original versus?
That's original is the one he actually built for the study we talked about in the beginning.
Oh,
He simply
okay.
just did by hand. This is the best I can do on this FPGA.
It has no off-chip memory at
Yeah,
all.
yeah. Okay, so actually, all of these we don't pay attention to off-chip memory. Actually, yeah, I think I mentioned. I mentioned it before, but I'll point out again. Right, we didn't put in an NOC yet. Right, there's no NOC. NOC for sure. We just right. If you try to NOC in solved logic, right, not going to work. Okay. So that's some of our new results on the clusters, and actually, so what Eric's doing right now is looking at this control program issue, and so here we have so this option of let's keep it soft, right? So and soft actually has two interpretations. I can take control thread and compile directly to logic, okay, or I can also compile to soft cores. They're both soft. Right, but one is software, one is hardware, right? And then I can also imagine if I actually build actual device, maybe I do put in a hard microcontroller. I can run a whole lot faster and take a lot less area than this. Okay, and so here, he's actually building a compiler for generating this logic, and hopefully pretty soon we'll be able to actually do a comparison between the overhead of this versus this, right? And also kind of figure out, kind of get a quantitative comparison between these two things. It's actually not clear, and at first look it's not clear, because, right, this turned out to be, like this, you can imagine very, very cheap in terms of area, right? This is not cheap in area to compile these controls to finite state machines, especially when things become, big data size and very elaborate controls. Okay, so the verdict's still out on this particular comparison. Maybe we'll see this, sometime next year. Okay, that's all I have. So I'll conclude and lectures here. Perfect. Right. So I think the point I'm trying to make in the beginning is that I think we, whatever happens in the future, I think we need to look. Right. We need to look beyond general purpose, because general purpose is not going to give you faster for less power. That will grow at a certain trend. If you want to break that, you got to go right. GPU, something with more parallel, more specialization, to not pay the general purpose overhead. And in doing so, I think remember that power, I think that it is a first class design constraint that we have to meet, right? It's performance area, power is as important as those things, right? And I think sort of change our mindset about what FPGA is good at, right? Floating points within reach. FPGAs are good at floating points. Double precision costs a lot more. Single precision, quite good, right? And what we need for FPGA to become, viable is really to make it much easier to use than it is today. And I talk a whole lot about the CORAM architecture, kind of to address, right, this usability and portability issues so that we can sort of harness the power of that FPGA. And the last thing is I'm going to make two other points before I quit. And this is because I get asked this question all the time, right? People object to FPGA because they say software is easy, hardware is hard. Okay? Don't ever let them get away with it. Okay? The people, most of the time when people come tell me, oh, software is easy, what they're thinking is, hello world. It's really easy to write hello world in software. And you imagine a big part of that, it's not that software is easy, is, when you write hello world in C, you get the C libraries, you get the system calls, printfs, all the IO, that's all virtualized for you. Okay, that's what makes it easy, right? And I think CORAM is trying to provide some of that, something like that for FPGA, okay? And the other thing is, even in an absolute sense, right, if you start talking about trying to tune, FFT, major multiplication, if you want to get peak performance out of multi-core CPUs or GPUs, those are PhD theses. There's nothing easy about that either, right? So I think people really, when people start comparing, is software easy, is hardware hard, you really have to make sure we're talking apples to apples. Okay, so I'll just leave you with that, and that's all I have. If we have time, we can take some questions, or we can get some food first, and
We can ask
we
a few
talk,
questions.
ask questions
Yeah.
over pizza.
Let's thank our speaker. Thanks. Really good. Take a few questions. We might have some online. I don't know if anybody's asking questions online. Not.
I think you first.
So block matrix multiplier is a good example where you would probably reuse a lot of input data in different
Right.
CORAMs. So do you envision some kind of cache, especially if you're hardwired?
Yeah. Well, okay. So actually, I don't have the backups like this version. So right. Actually, if you read the paper, we have such notion what's called personalities. Right. So we give you, this is kind of like C libraries. We give you CORAM, but we can also give you library of both soft logic and control thread that makes it behave like certain things. Something like a FIFO, something like a cache if you want.
But that means using your CORAM, your local SRAM as a cache.
Right, using local SRAM and using the control thread to mimic the effect of a cache. Actually, in the block show example, we do that. So no, in sparse matrix data multiplication, we had to do that to cache things. Right? The idea is that even then, it's not every designer comes along and build my own cache. It comes as a C library-like thing with the CORAM abstraction. So I think I could be answered. 1, 2, 3.
As partly a suggestion, maybe partly a question.
Yeah.
So there are network on chip and system design tools from commercial vendors. So I'm most familiar with Alteros, which is the
Right.
network on chip design tool is QSYS.
Right.
And it will build a soft network with any topology you want.
Right.
And you can put a soft processor in there as well.
That's right.
And that is a relatively common method to basically abstract RAM. Like it's a useful method to abstract RAM. I'd say right now it hasn't been used for the highest performance systems yet, so it's not really
Right.
proven that you can use that for everything. But that might be a good way to try to prove out this methodology on existing FPGAs.
Right.
Rather than writing it all in HDL, which is hard,
Right.
basically define your buses in your network on the chip in that at that layer of abstraction. You can also define multiple masters to memory on chip and off chip. So basically, you can have data being transferred in by a CPU, a custom DMA
Right.
unit, custom units that you might design the soft logic, anything you want, put into on-chip memory, and then other ports through that network on chip accessing that for your computational units. So it doesn't give you, it's a lower level abstraction than what you're doing, but it gets you partway there. So that might be a good way to, by combining those two things, you might be able to get results earlier, like
Right.
put the framework together, and you'll get results of what happens with the soft fabric, which might be very interesting.
No, I think philosophically we're exactly in the same place, right? We're not going to give real devices anytime, real CORAMs anytime soon. Let's prove it out using soft logic, and let's make sure we apply the right interpretation so things are meaningful. And I think what you said it actually makes a lot of sense, right? We're definitely not into reinventing the wheel. And also, just imagine this gets into this CORAM is architecture, and on Altera, that could be exactly the right thing to do. You build CORAM using all the existing Altera stuff. Right. So I think that's something we'll definitely look into.
Yeah, I think it'd be
Right.
very
But I
interesting to
think
see the
it's definitely, it's philosophically we're in the same place. Right?
It allows
We're
you
gonna
to-
understand a little bit better before we go build and ship.
Sure. It also allows you to customize the network. I mean, obviously, as you pointed out, you're gonna lose a lot, but it's a soft logic.
Right.
But because you're working at that, what are my bus masters, what is my network protocol, it's relatively easy for you to customize.
That's
So
right.
it makes it much easier for you to try to gain back by changing what is the network. Whereas if you're building a whole underlying implementation, it might be quite difficult for you to build enough different implementations such that you can get fuller leverage.
Right, and I think part of us building the prototype is so that we can actually explore and study all the details, right? But it just, I think the NOC, that element specifically, I think that's one place where we're pretty sure today, if we get our way, right, if this really becomes the chip we build, right? I mean, that's kind of one of the prime, like memory controllers, right? I think NOC has the right flavor that to put in, right? Just put in hard logic, right? Because, and forget about, don't worry, there are no long routes anymore, right? It's always,
We'll take it offline. I actually think
Right.
that's an interesting question.
because we're not really building FPGAs anymore in a
Yeah.
sense, right? I mean, it's a reconfigurable fabric processor or something. But I think I understand the question.
So early on, you described having a kernel and then putting some memory steering logic
Okay.
around that. But one of the things I didn't quite see in the slides was how you intended to get data into the FPGA from an external interface. So for instance, if it's plugged into a CPU bus or a PCI Express bus,
Right.
are the control threads going to manage the data flow for those interfaces as well?
Or how do I get back into presentation? Right, so we have what we call some fabric and non-fabric, kind of like core uncore, right? So the bulk of what we talked about today is, right, the question of how do you present main memory, external memory to these kernels, right? To a CPU, you do loads and store to share memory. That's how you think, right? That's not good for kernels, right? So this abstraction is how do you present memory to the stuff in the fabric? In terms of how do you bring memory, high performance memory to the edge of the fabric, I actually think we can do exactly, we don't have to do something very different, right? We can do, right, we hardwire the memory controllers. You can even imagine having multiple levels of caches. You can even imagine having virtual memory, vanilla virtual memory, right? So you have again, just have a linear address space at the edge of the fabric. That part, doesn't have to be different, right? What's really different is, okay, now that I actually have performance, memory performance at the edge of the fabric, how do I make that, how do I have the kernels, what is the abstraction for the kernel to interact with that? And that's this CORAM and this thread. Okay, but so I think if I understand your question correctly, up to the edge of the fabric, we can do what we know how to do. Right? Yeah.
I guess something along the lines. How will you keep the coherency between the SRAM memory and the cache in the CPU of an x86 processor in the same machine?
So I think we haven't thought about a problem. We thought about it a little bit. I'm winging the answer right now, right? So, right, on the inside, I don't care. There's no coherence. There's no notion of coherence on the inside, right? But you can sort of imagine up to here having a cache coherent cache all the way up to the edge of the fabric. Once you're inside, we're making a copy of it. It's not a cache copy of memory location. It's a copy of the data that you grab from the address space. So we don't, at least the way we're thinking right now, we're not extending. We're not thinking about extending cache coherence into the fabric, but on the way out, you can do standard stuff. Now, going back to that personality stuff, you really wanted, it's possible we can build, right? We can build personalities to make that happen. It would be expensive, but it's not, you know, with soft logic we can do it. But in terms of the native abstraction itself, right? It's not load and storage. We're copying data. Okay. There was a question here that disappeared.
Oh, yeah, sorry. I was going to ask about, well, you talked about the constraints of various different devices for computation, so
Right.
GPUs and so on, and how power is going to be increasingly constrained. You didn't really mention cost. And like currently, I mean, like a basic 760 is probably an order of magnitude more expensive than a GPU, but it probably doesn't offer an order of magnitude more performance currently.
For that, I kind of use area as a normalizer. I think cost has a lot of other factors built into it.
Sure.
Right. So I think if you think, think in terms of performance per area, right? That kind of give you a not perfect, but a more linear approximation of cost.
Sure. So I mean, if you look far enough out in the future, cost really just boils down to die area.
Right. Imagine when things become really commodity, right? It's just how much glass do you want to buy?
But there's a big gap between the existing state of affairs and the
Sure.
large commodity.
Sure.
You have to do something to fill that gap to motivate increasing sales to reach that.
That's right. I mean, so I mean, this is a research that will happen in 5 years. And so I think, and who knows what will happen in 10 years, despite what ITRs tells us. We'll probably, I think, maybe we'll, so yeah, but that's something, so cost is, dollar cost is very
I was just curious, towards the end, you were talking about the implementation of the control threads in soft finite state machines, soft processors, and hard processors.
hard process.
And you commented that so far you think the soft finite state machines were quite large. And what sort of thing about
No,
this?
compared to compiling the soft cores.
Yeah, into a soft processor.
Yeah, because
code into a
if
soft
you look
processor.
at both the Xilinx Altera, the soft microprocessor, if you take the simplest, right, the simplest instance of that, they're really small.
Yeah, 1,000 or 2,000.
So in terms of
elements, right?
actually, and so in terms of comparing area, right, compiling code to logic, you're probably not going to win. It's at least proportional, because it now becomes proportional to code size, you see. Right, but performance is different, right? Because when you map thread to logic directly, they'll go much faster. We go one basic block at a time.
Yeah, for sure, the performance.
Right,
is
but in
different.
terms of area, rather than having a fixed area, iterating over it, right, now it's going to cost us.
I was just even surprised about that, because I was thinking the kind of finite state machines you're talking about didn't seem that complicated, so I would have thought they would be
Well,
pretty small.
But these are examples, right? I think you can, but it's just at least it's just but you do agree it's proportional to the code,
To the
size
size of the logic is proportional to
to the static program size.
Yeah, yeah.
Right, and so if you start building not toy benchmarks, real applications, it can easily cross over. There's not much headroom, right? For this kind of stuff, it is small. Actually, so okay, for the stuff I showed you, it does come out smaller.
Even the Black-Scholes one?
Yeah, right, but the Black-Scholes is really easy. It's just streaming and streaming out, right? But what we saw is that there's not much headroom, right? Because mostly because these solid processors are really cheap. They did a really good job making this small.
Any other questions?
I think we need pizza.
Okay, well, thank our speaker again. Thanks a lot.
Thank you.